You already know what you'd expect to happen if you fell into space. Your body exploding, your blood boiling, the cold snapping you solid like glass. Every movie has told you this, and movies are usually wrong about the actual part, which is that the thing that kills you does it in a way your brain did not predict. And that wrong prediction is the thing you cannot stop thinking about once you notice it, which is, I came across this problem while reading about a test accident in 1966. A technician at NASA Houston, a person whose name I never learned, was inside a spacesuit during a pressure test. The suit failed. The chamber decompressed to vacuum in seconds, and he was exposed to nothing. Not cold, not wind, not pressure. Nothing. And I thought, okay, this is where it gets bad. This is where the movies were right. But then I kept reading, and the thing that stopped me was this. When they brought the pressure back up, 30 seconds later, he woke up. He was fine. He'd been unconscious for half a minute in the hardest environment a human body can encounter, and he recovered with no serious injury. I spent 3 hours trying to understand how that was possible. And the reason I kept going wasn't that I wanted to know how to survive vacuum. It was that I couldn't stop trying to answer a question that seemed too simple to be the thing nobody had answered yet. Why does the body handle the thing we think should kill it faster than it should be able to? And what actually does the killing? Here's what most people believe. And I want to be clear that what most people believe is not wrong. It's just incomplete in a specific direction. They believe that vacuum is a kind of environment, cold, empty, hostile. That exposure to it is like being exposed to extreme altitude or deep water, a problem of external pressure pushing on you. What the research actually shows is something that contains that belief the way a larger shape contains a smaller one. The pressure is still part of it, still true, still happening, but it's not the main problem. The main problem is something that happens inside you, which is the part that doesn't feel like an answer when you first hear it, because answers are supposed to resolve uncertainty, and this resolves nothing except to point at a harder question. The thing that matters most isn't what's outside, it's what stops being outside and starts being inside, which requires accepting that your body isn't a sealed container the way you've been assuming it is. That's the framework. First, what everyone knows. Second, what the evidence actually shows, which is that the evidence contains the first part but doesn't stop there. Third, the part that's almost never discussed, because it's the part that makes you realize the first two parts were just the entrance to something stranger. When you fall into vacuum, 3 things happen in immediate sequence. The first is mechanical. The air in your lungs wants to escape, and it escapes at the speed of sound. If you're unlucky enough to hold your breath during this, the pressure inside your chest builds until your lungs rupture, and you die in a way that is genuinely explosive. Air bubbles the size of grapes moving through your blood, lodging in your heart, in your brain. That's the catastrophic decompression event. That's the thing that actually is explosive. And this is where most people stop paying attention. That's not what kills you if you don't hold your breath. If you let the air out, if you do the one counterintuitive thing your panicking body will scream at you not to do. You survive the rupture of your lungs. You survive it because the pressure equalizes. You just give the air somewhere to go. So decompression itself, the mechanical event, that's survivable. The thing that comes next is not. Your body is approximately 60% water. Water has a boiling point, the temperature at which liquid turns into vapor. At sea level, that's 212 degrees Fahrenheit, but boiling point isn't fixed. It depends on pressure. The higher the pressure, the harder it is for water to escape into vapor form. The lower the pressure, the easier it becomes. And in vacuum, the boiling point of water drops so low that it reaches your body temperature. Your body temperature, the water in your mouth, your throat, your soft tissues, it doesn't need to be heated. The pressure drop does the heating, or rather, does the opposite of heating. It allows evaporation to happen at a temperature where evaporation should be impossible. This is called ebullition, not boiling technically. The water doesn't bubble violently like it does in a pot. It's something quieter and worse. Water vapor forms rapidly in your soft tissues, in your saliva, in the fluid in your eyes. Your mouth and nose cool to near freezing as the water evaporates away. Your body swells. Estimates are that you'd swell to perhaps twice your normal volume unless something is restraining you. And this happens within a few seconds. Your body is undergoing a phase change, turning from solid to something closer to foam. But you don't feel most of it. This is the part that breaks the expected narrative. When you're exposed to vacuum, you lose consciousness long before the swelling becomes severe. The research on this comes from military aviation, from pilots who experienced rapid decompression at high altitude. The time of useful consciousness, the amount of time your brain remains functional, is about 9 to 12 seconds above 50,000 feet. In vacuum, it's roughly the same. 10 seconds, maybe 12 if you're sitting still and not panicking. 5 if you're moving, if adrenaline is flooding your system and your muscles are burning oxygen like a fire. You have 10 seconds to help yourself. And in those 10 seconds, you can't do much more than experience the sensation of knowing something has gone very wrong. Your body doesn't produce pain in vacuum the way you'd expect. The water evaporating from your skin produces a cooling sensation, like wind, like pressure. The gas expanding in your stomach produces discomfort, the kind of internal pressure that doesn't quite qualify as agony. But the thing that actually incapacitates you isn't pain, it's hypoxia, the simple cascading failure of oxygen delivery to your brain. When the air leaves your lungs, the oxygen in your blood has nowhere to go. Normally, oxygen moves from your lungs into your blood. When there's no lung air, when there's vacuum above your blood, oxygen moves backward. It moves out of your blood into the space where your lungs are. You're not suffocating because there's no air to breathe. You're suffocating because the air that was inside you is leaving and is taking your oxygen with it. This happens in seconds. By 10 seconds, your brain has lost enough oxygen that conscious thought becomes impossible. Your vision darkens, you might experience a sensation called the gray out, where the world loses color, then black, then nothing. Your heart keeps beating for another 30 or 40 seconds. Your brain remains partially alive, though unconscious for another minute or so. But you, the conscious part, the part that experiences falling, the part that knows what's happening, that ends in the time it takes to sing the first line of a song. And this is where I need to tell you what I got wrong initially. I thought the problem was how fast you die. I spent days looking at timelines, at the precise sequence of cascading failures. But timing isn't the problem. The problem is that if someone finds you in those first 30 seconds, if someone reaches you before your heart stops, you can be saved. The technician in 1966 lost consciousness in 12 seconds. He was recompressed after about 30 seconds. He woke up. His lungs had begun to tear. His body had swollen. His blood was beginning to boil. And still, recompression stopped it. Stopped all of it. His body had shifted partway into a state it shouldn't be able to return from. And it returned from it anyway. This creates a specific problem for the concept of vacuum as a killing environment. It's not quick. It's not clean. It's not even reliably fatal if the exposure is short enough. And that contradiction, that something can cause this much damage and still not be a sure kill, is where the actual darkness lives. Because it means the line between survival and death isn't the environment, it's time, it's proximity to rescue. It's whether anyone is nearby with the knowledge and equipment to reverse what's already begun. Let me describe what happens in those first minutes with more precision, because the precision matters. When you lose pressure suddenly, your body doesn't react as a unified system. Different parts fail at different rates. Your lungs expand immediately, and if your airway is open, the air escapes and the pressure equalizes within your chest in less than a second. Your blood doesn't boil because your veins and arteries are elastic. They hold enough pressure that even at your blood's current temperature, vapor forms slowly at first, mostly at the edges of small blood vessels, small bubbles in a liquid that's still mostly liquid. Your consciousness fades in those 9 to 12 seconds because your brain is starving for oxygen, not because your brain is boiling. You're not experiencing the full suite of vacuum effects. You're experiencing hypoxia first, and the hypoxia wins before the other effects get bad enough to matter. But hypoxia is deceptive as a killer. It's not painful, it's not obvious, and crucially, it's reversible if you catch it early enough. If you recompress within 30 seconds, while your body is still mostly intact, while the vapor bubbles in your blood are still small, while your swelling is still partial, your body can handle the reversal. The water that evaporated can condense again, the bubbles can collapse, the tissues that swelled can contract. Your brain, starved of oxygen, can wake up and remember how to function. The deeper problem is the one that doesn't resolve itself on those timescales. When your body swells in vacuum, when water is evaporating from your soft tissues, you're not just losing water, You're losing salts, proteins, everything that was dissolved in that water. And when you recompress, when that water condenses again, the things that were in it don't always find their way back. Some of that water re-enters the cells that lost it, some doesn't. The osmotic balance is disrupted. And this is where I need to be precise about what the old NASA data was actually saying, because I misread it the first time, or rather, I read it correctly and then didn't understand what it meant. The Bioastronautics data book, which is the foundational source for all of this, describes exposure to vacuum with a flatness that makes it sound almost manageable. Some degree of consciousness will probably be retained for 9 to 11 seconds. That sentence means that in 9 seconds, you're already partially paralyzed. Paralysis will be followed by generalized convulsions and paralysis once again. That means your body will seize, water vapor will form rapidly in soft tissues, which means your skin, your organs, your nervous tissue, all of it is transitioning into a different physical state. And it says it is very unlikely that a human suddenly exposed to a vacuum would have more than 5 to 10 seconds to help himself. 5 to 10 seconds, not to rescue yourself, not to call for help, to help yourself, to do anything. And then it says this: if immediate help is at hand, although one's appearance and condition will be grave, it is reasonable to assume that recompression to a tolerable pressure within 60 to 90 seconds could result in survival, and possibly in rather rapid recovery. This is the point where the problem stops being a question about the environment and becomes a question about time and proximity and chance. The same exposure that ought to be unsurvivable becomes survivable if someone is close enough. The person you're with becomes more important than the place you're in. And that's a different kind of death sentence, because it means you can't die alone in space the way fiction suggests. You can only die alone in space if no one sees you fall. You might be thinking that this only matters in spacecraft, in scenarios where rescue is theoretically possible. And you're right to think that. Deep space isn't spacecraft. If you fell out of a ship orbiting Earth, rescue is possible. If you somehow ended up floating in the void between stars, rescue is not. But the reason I'm focusing on the rescue possible scenario is that it reveals something about the mechanism. It reveals that vacuum doesn't kill you through any single catastrophic effect. It's a cascade. You lose consciousness before you die. Your body undergoes several simultaneous failures, each on a different time scale. Your lungs are destroyed in a second. Your consciousness is gone in 10. Your heart is still beating at 30. And your brain is still electrically active at 60. And at 90 seconds, if your pressure is restored, most of that can be undone. What can't always be undone is harder to quantify. The cases that survived showed occasional neurological problems immediately after recompression, blindness, vision defects, problems with coordination. Some of these went away quickly, some didn't. There's a case of a dog that survived vacuum exposure for 2 minutes and recovered with no apparent damage. There's a case of a human who survived about 30 seconds in a suit test and woke up fine. And then there are the cases where recompression brought the heart back and the lungs back and the brain back, and something more subtle was wrong. Something in the biochemistry, something in the way the cells were organized after the osmotic shock of having water ripped out of them and forced back in again. Something that medicine in 1968 couldn't quite identify and isn't sure it can identify now. This is where you have to zoom out and ask why this question exists as a question at all. We spend enormous resources preparing for crewed spaceflight. We study vacuum exposure because astronauts need to do spacewalks, because there will always be a chance of suit failure, because the costs of that scenario are real and immediate. And in the process of that research, in the process of creating protocols and testing equipment and studying animal subjects and, yes, analyzing the rare human incidents, we accumulated this knowledge that says vacuum exposure is not the instant death sentence that intuition suggests. It's slower, it's more complicated. It's survivable if you're lucky about timing. It's lethal if you're not. But the lethality isn't built into the environment itself. The lethality is built into the isolation. And that's a distinction that changes how you have to think about the danger. The worst part of falling into deep space, if you fall into it alone, isn't what happens to your body in the first minute. It's the isolation that means no one is finding you in the first minute. It's the knowledge, if you somehow retained consciousness for long enough to know it, that no rescue is coming, that no pressure vessel is racing toward you, that the cascade of failures will continue uninterrupted all the way to the end. You probably expected this explanation to start wrapping up by now. I thought it would too, at about this point in my research. But what I kept finding was that the straightforward account, the timeline of what happens to your body, that's the part that's relatively well understood. The research is solid. The mechanisms are clear. What isn't well understood is something that sounds simpler but turns out not to be simple at all. What would you experience during those 10 seconds? Most of our knowledge about consciousness during hypoxia comes from people who recovered. Pilots who experienced decompression, who survived because they were wearing oxygen masks or because the pressure was restored, they reported a sensation. They called it the gray out, not blackness, not pain, a dimming, a sensation of the world losing detail, of colors desaturating, of time becoming strange, and then nothing, then waking up. But there's a gap in that testimony. There's the gap between the gray out and the unconsciousness. There's the part where your brain is still partially functional, but losing the threads of perception and thought. There's the part where you're still conscious, but can't hold a coherent thought. And we don't know what that's like because the only people who'd know that are the people who didn't survive. This is a little like, and the analogy falls apart here, which is actually the point, like trying to describe the texture of silence to someone who has only ever experienced it as the absence of something they wanted to hear We can describe the silence that comes after a loud noise stops. We can measure how long it lasts. We can describe what happens to sound when it disappears. But we can't describe what it feels like to experience silence as silence without a reference point. And similarly, we can describe what happens to your body when you lose consciousness in vacuum. We can measure it, we can predict it, we can even, in some limited way, survive it. But we can't describe what it feels like to fall into nothing, to feel your consciousness fragmenting while you're still aware that it's fragmenting, because if you experience that and if you don't survive it, you never get the chance to report back. The thing I did not expect when I started is that everything I just described, the mechanism, the timelines, the feedback loops, the physiological cascade, that's the part that's relatively well understood. The part that's not well understood sounds, when you first hear it, like it should be simple. It has the structure of a simple question. What does it feel like? But it has resisted simple answers for a surprisingly long time. And I think the reason it has resisted them is that we keep trying to answer it from inside the framework of the person experiencing it. And the problem is actually about the framework itself. We're asking, how does the body experience vacuum? And the assumption built into that question is that the body's experience is something continuous, something that can be reported, something that survives into memory. But what if it doesn't? What if the experience of falling into vacuum is, by definition, unmemorable? Not because it's traumatic and forgotten, but because the consciousness that would do the remembering is already gone before the worst parts begin. Let me return to something I mentioned earlier about the 1966 case. The NASA technician. I said he lost consciousness in 12 to 15 seconds. I want to be more precise about what we know and don't know about those seconds. When the pressure dropped, he was aware enough to notice something was wrong. His body registered the stress, his heart rate changed, his lungs began their emergency exhalation. He had enough time to experience fear, possibly, or surprise. He had enough time for his autonomic nervous system to respond. And then, somewhere in the range of 10 to 15 seconds, it was over. His brain had received enough warning that something catastrophic was happening, but not enough time to process what. The experience was not, I am in vacuum, followed by I am dying, followed by I am dead. It was, something is very wrong, followed by black. And then nothing for 30 seconds. His body went through all of the changes I described. His lungs expanded, his tissues swelled, his blood began to boil in the microscopic sense, vapor forming in the small spaces between cells. His heart kept beating because the heart beats on its own rhythm, independent of conscious direction. And when the pressure came back, when the technician's colleagues outside the chamber realized what had happened and flooded it with air again, the process began to reverse. He woke up in an odd state. He was conscious, but his body didn't feel like his body. His hand was swollen. His mouth felt like it had been through a fire and then frozen. His chest hurt, though not as badly as it should have. The swelling went down, the pain faded. Within hours, he was largely fine. though I'm sure something stayed with him, some knowledge of those 30 seconds that he wasn't there to experience. The way your body remembered falling when your mind did not. The specific quality of that absence, the falling that you don't experience, is, I think, the honest place to stop exploring the mechanism. Because the mechanism is knowable. We have the data. We know what happens when the pressure drops. We know the sequence of failures. We know the timeline of survival and death. And yet, knowing all of that doesn't actually resolve the question of what it's like. It just clarifies that the question might not have an answer because the experience might not have an experiencer. So I'm back where I started, more or less. That expectation you had that your body would explode, that you'd freeze, that you'd feel it happening. I understand it better now in the ways that can be made precise, and I understand it less in the ways that cannot. Because the reality is, stranger in a particular direction, your body wouldn't explode, it would swell, you wouldn't freeze. You'd cool, but more like air conditioning than ice. You would feel something for about 10 seconds, and then you wouldn't feel anything at all. And by the time you'd feel something again, if you ever did, the worst would be over or you'd be dead. And that would be a different problem entirely. That is usually what happens when you follow something far enough in. The question gets cleaner, the discomfort gets worse. You know more about how the machine works, and you understand less about what it's like to be inside the machine while it breaks down. You learn the technical terms for every failure, and you realize that knowing the terms doesn't actually tell you what it feels like to experience the failure. You map the timeline of unconsciousness, and you understand that you'll never actually know what that period contains because consciousness, by definition, wasn't there to record it. The vacuum of space isn't cold, isn't hostile, isn't actively trying to kill you. It's simply the absence of the conditions that keep you alive. And your body's attempt to exist in that absence is all mechanics and biochemistry. All involuntary responses that happen whether you're there to experience them or not. And maybe that's worse than the movie version. Maybe the unknown is darker than the dramatic version could ever be. I think that is probably the honest place to stop for now.